All right, so chapter 8. We have that we want to solve the following triangle using either the law of sine or the law of cosines. In this case, we have our starting values. B is equal to 11, C is equal to 17, and capital A is equal to 65 degrees. So we know B and C are going to be our sides when A is a angle measurement. So we can first establish what kind of triangle this is. We have B is equal to 11, C is equal to 17, capital A is equal to 65 degrees. Our side A is going to be opposite of our angle A, which means that if it is opposite of our angle A, that means the two sides that are connecting our angle A are going to be B and C, which tells us that this is going to be a side angle side triangle. Establishing this fact isn't always necessary to the problem, but it can be helpful. We could also draw an image with this picture if we would like, if that would end up help us, or that would end up helping us work out our problem. So let me draw that triangle real quick. All right, so we're given our angle A, which is 65 degrees. We're given our value of C, which is 17. Let's see. And our value of B, which was 11. So the values we're searching for are going to be angle C, angle B, and side A. So we can see this is going to be a side angle side triangle. We've drawn out what this is going to end up looking like. And now we just want to determine if it's going to be easier to use law of sines or the law of cosines. So with SAS triangles, we can either use law of sines or the law of cosines. So we can use either one in this case. But considering that we have two side lengths and an angle, it'll be easier for us to use the law of cosines. The law of sines, remember, tells us that sine of angle A divided by side length A is equal to the sine of angle measurement B divided by the side length B, which is also equal to sine of the angle C divided by the side length C. So we don't exactly have all the pieces to use the law of sines, and the law of cosine uses basically two sides at an angle, which is exactly what we have. So it's going to be easier for us to use the law of cosines. So we can say using the law of cosines will allow us to solve for side length A when given B, C, and angle A. So because we have side lengths B and C and our angle A, we can go ahead and easily solve for our side length A, which would then allow us to easily solve for the rest of the angle measurements. So remember the law of cosines. Tells us that A squared is going to be equal to B squared plus C squared minus 2 times BC times sine of angle A. So now we just want to plug in all of these values. So B is 11. So we have 11 squared plus C is 17. So 17 squared minus 2 times 11 times 17 times sine of 65 degrees. So at this point, if you have a calculator, you can by all means plug this value into a calculator at this point and then just take the square root. Or we can go ahead and solve for each value. So 11 squared is going to be 121. 17 squared is going to be 289. 2 times 11 times 17 is going to be 374. And then we have times sine of 65 degrees. using a calculator to find the value of sine of 65 degrees and trying not to round as much as possible is going to be the way you'll get the closest part of your answer. So just simplifying this, we get 510 minus 374 times sine of 65 degrees. And we find A by taking the square root of this value. So trying not to round as much as possible so we can get the most accurate value of A. When we plug this value into a calculator, we get that A is going to be equal to about 13.08. So this is one of our values. We've now found our value for side length A. And now what this allows us to do is that we can now use the law of sines. So we're switching over. You can continue using the law of cosines, but to just find angle measurements, it will be a little bit more difficult just to solve for an angle measurement. We're using the law of sines now. It's going to be much easier since we do know an angle and its matching side length. So you can now solve for angles B and C using the law of sines. Remember our law of sines. My cat is being very needy right now. So remember the law of sines tells us that if we have sine of angle A divided by the side length A, this is going to be equal to sine of angle B divided by the side length B, which is also equal to sine of angle C divided by side length C. So let's write the law of sines. So let's go ahead and solve for, running out of room here. Go ahead and solve for angle B first. If we solve for angle B first, this means that we're going to get sine of 65 degrees divided by 13.08. It's going to be equal to sine of B divided by 11. Now, if we solve for B in this case, B will end up giving us sine inverse of 11 times sine of 65 degrees divided by 13.08. Which in this case, if we go ahead and use a calculator, which we'll definitely want to do at this point, we'll end up getting the value of B being 49.7 degrees. So since we have our value of B and our value of A, we can easily find C. So we can find C by the fact that A plus B plus C is equal to 180 degrees, where we have 65 degrees plus 49.7 degrees plus C is equal to 180 degrees. Adding these values up, we get that we have 114.7 degrees plus C is equal to 180 degrees. So solving for C, we get that C is equal to 65.3 degrees. And we'll just really quickly scoot our next problem down a little bit. Just a line or two here. There we go. So we have all of our values. And now we just want to sum it up. So thus, we have our side length A is equal to 13.08. Our angle B is about 49.7 degrees, and our angle C is about 65.3 degrees. And that there is our answer. So we solved for all the bits that we were trying to solve for. It helped by identifying that this was an SAS triangle because we can solve SAS triangles using the law of sines or the law of cosines. So we could use both, which we did, and it ended up helping us quite a bit in order to use both. All right, on to problem 4, which is from chapter 9. So number 4 states that the vector v has an initial point P and a terminal point Q. We want to write v, the vector v, in the form of a times I plus b times j. That is, we want to find the position vector. So this is, I just realized my semicolon looks incredibly like a j. So let's just rewrite that real quick. So this is BJ, and we'll put a comma there instead. I realized that they looked the exact same. So A times I plus B times J, that is that we just want to find the position vector, where we have that P is equal to 0, 0, so the origin, and Q is equal to 13, comma 5. So we can state that we know if we have an initial point, which we will label P, this is equal to x1 comma y1. And if we have a terminal point, which we'll label Q, this is equal to x2 comma y2. It's the second point essentially. So we label the x and y terms with sub 2's and then sub 1's for our initial point. And it has the vector v going through these points such that the position vector is vector v is equal to x2 minus x1 times I plus y2 minus y1 times j. So knowing that our position vector is going to be of the form of x2 minus x1 times I plus y2 minus y1 times j, we already know that 0, 0 is x1, y1, and 13, 5 is our x2, y2. So we already know the values of our x1s, x1 and y1 and our x2 and y2. So we can just plug this in. So we can say this, vector v is equal to x2, which is 13, minus x1, which is 0, times I, plus y2, which is 5, minus y1, which is 0, times j, which just ends up giving us the form of 13I plus 5j. And that would be our answer there. So you're essentially just subtracting the x and y terms of your terminal point from the x and y terms of your initial point. So you're just subtracting the other way around. You're subtracting your initial points with the x, y terms. You're subtracting those x, y terms from the xy terms of the terminal point, and then rewriting them in this form where you multiply your x terms by I, or the difference of your x terms by I, and the difference of your y terms by j.